Hello, everyone. My name is Chesnais. I'm a staff software engineer on LinkedIn, and I'm here to talk to you about what it was like to design and operate an xDS control plane for the LinkedIn scale. So first, a little bit of background as to why we're here and what we're doing at LinkedIn. LinkedIn's not much of a gRPC shop just yet, but we're making big efforts in that direction with Envoy and gRPC proxyless, which I'll talk about in a second. Today, everything is built on top of our own stack, which is called RESTly, which is basically just a REST JSON framework. And the control plane for RESTly is Zookeeper. What that means is that Zookeeper stores all of the service discovery configurations, such as routes, load balancing parameters, timeouts, etc. Each server registers itself to Zookeeper by adding an ephemeral Z node in the corresponding cluster. And then clients then set watches on those clusters and then get notified whenever the cluster changes. This way, when they're trying to send requests to a specific service, they look up the cluster that that service belongs to and then get a host list directly from Zookeeper. So, but for those of you who don't already know this, Zookeeper's got a bit of a tendency to blow up whenever you least expect it. So as we're making a push to gRPC and Envoy, we decided to develop our own xDS control plane that could speak both to Envoy and gRPC, but also to the old RESTly clients. This way, we could reduce the load on Zookeeper by having the RESTly clients talk to the xDS control plane. And the way that we did this was basically replacing the Zookeeper connection in those clients with the gRPC XDS connection to the control plane and having the control plane return basically the Zookeeper data that it was used to. So what even is XDS anyway? And it's probably a term you've heard a couple of times today, but what it is that it's the configuration for Envoy. And it's got two components. It's a set of proto schemas which define the service discovery configuration, or otherwise known as resources, and a protocol for subscribing to and then receiving updates on those resources. A little bit more terminology. The DS in XDS stands for discovery service, and then the X stands for the resource type that's being discovered. So CDS stands for cluster discovery service, or RDS is route discovery service. It's supported natively by gRPC, and what I mean by that is that a gRPC client can directly talk to the XDS control plane and will behave exactly like Envoy, except without having to have that proxy in the middle. So you basically configure both Envoy and gRPC to just talk to the same XDS control plane. So what do we want the stack to look like as we migrate to gRPC? As I mentioned before, the new XDS control plane can support all three client types. So RESTly talking and getting the Zookeeper data from the XDS control plane, while the gRPC and Envoy clients get the corresponding Envoy configuration or XDS configuration. The cluster registration, which used to happen over Zookeeper, now happens over Kafka because it's much more scalable. And in the future, as we're migrating towards Kubernetes, we're hoping to just completely get rid of, or almost completely get rid of the Kafka registration service, because most services don't have to have complex registration logic. They just say, hey, I'm this service, just send me some traffic. So how does this talk apply to you? The RESTly clients and the gRPC and Envoy clients are all using the same settings when they're opening the XDS stream, the gRPC stream to the XDS control plane. So at this point, we can effectively treat all of those clients as behaving the same. So at this point, this sort of becomes the abstract problem of scaling out the XDS control plane for any large service or any large company, and everything at this point should be applicable to all of you. So start rolling it out. Again, everything has got the default settings, and start to see some pretty weird traffic distribution. We've got some hosts here taking 10 times the traffic of pretty much the rest of the average. In this case, 100K is 100 clients each requesting and receiving resources. So this is actually really high load, and it was sort of revealed that we really have to make sure that the implementation of the XDS control plane is as efficient and as performant as possible, which I'll talk about a little bit later on. But yeah, so what's happening here is that the default setting for gRPC is the pick first strategy. Pick first strategy just picks the first IP it gets from the DNS record, which at LinkedIn, the DNS records are shuffled every 3 seconds, and that's what the TTL is. So we would expect that every single time it picks an IP, it should pick a random IP. So what's happening? Like, why aren't we getting just a more even distribution? So it's at this point, you guys get to meet my personal nemesis, RFC 3484, which corresponds to the IPv6 migration that was actually happening at the same time as we were rolling this out. See, little that you know, that when you ask for the ask the operating system, hey, what are the IPs for this DNS record? It'll, in IPv4, you get back the IP addresses in the order that are present in the record. In IPv6, you actually get them according to a very specific set of rules that are dictated by RFC 3484. And the way that this works is the IPs are sorted based on the target and how close it is to the source IP, so up to the first 64 bits. So you're basically just doing a longest prefix match. So you can see up on the board here, addresses 1 and 4 actually share the same prefix length, and they have the highest prefix length. So the client is going to try one of those two first before going down in the order of prefix length. So technically, you know, this is good. That's what you want, right? Because IPv6 addresses are roughly matching to sort of their geographical location. Each IPv6 segment is going to go like from, you know, continent, then country, then data center, then rack, et cetera. So you would expect it to still work roughly as expected. But what ends up happening is that there's some servers that are just closer than others. And no matter how many times we've shifted the hosts around, like taking them out of different racks and putting them somewhere else, it just always ended up that some hosts were taking significantly more traffic than the others. Okay, so how do we address this, right? Well, I guess this is ultimately the order in which it's going to get those, try those hosts. So at this point, we're kind of scrambling, right? We've got some hosts pretty much saturating the network cards, and then some other hosts are completely sitting idle. So we started looking at the gRPC docs, looking at sort of what's available, because we still own the REST client, so we can still make some changes there. And we see round robin. Okay, so how does round robin look? Let's take a quick look at what it looks like. It's supposed to iterate over all the subchannels, okay, and then send the next, just gonna pick a random offset into the list of subchannels that it has and start sending traffic to it there. Okay, so that's it. We just turn it on and talk over, right? You guys can go home. Not really, because it turns out there's a little piece of extra information that's needed. And it turns out round robin will eagerly create connections to every single target that it gets from the DNS resolution, which means that it's got hundreds of thousands of clients, each opening connections to the couple dozen XDS control plane hosts that we had. Wait a minute, really? What does that look like? So suddenly, got a couple hosts, as those changes are making their way through the system, we got a couple hosts inexplicably start running out of memory and crashing. So out of curiosity, I take a quick heap dump and I see this. For those of you who haven't had the pleasure of looking through Go heap dumps for hours on end, what we're looking at here is that about 80% of the overall heap is actually being used by effectively idle TLS buffers. And at this point, we had the entire fleet connecting to just a couple hosts, and we can't even scale it up, right? If we add a host, it add an extra record in the IP, or like an extra IP address in the record, and everybody connects to that host too, and it instantly runs out of memory. So we're pretty much screwed, right? We can't even add more hosts. We can't do anything. So yeah, I mean, sure, we had a great traffic distribution. Everything was perfectly balanced, but at what cost? We're getting completely overwhelmed. And the XDS streams, they're really long-living streams, so that traffic is basically just, once it's connected, it's there forever. So our only way out is just roll it back, go back to pick first, but now, I mean, we're back to square one, right? So what do? What we want is we want to limit the number of XDS streams that we have on each host, and that way we can hopefully avoid a massive skew in traffic. I mean, it's still going to be pretty bad. Some hosts are going to get more streams, but at least there's a limit. We can predict how they're going to behave. So we can't close the port on the gRPC port, because as soon as the limit is reached because the round robin hosts are going to be taking up all that capacity. So that's out of the question. So we have to look at what we can do at the protocol level. So at the xDS protocol, we can't really do anything. There's no way to tell a client to go away, and there's no way to do that at the gRPC layer either. So we got to look somewhere else. If we just close the xDS stream, what happens? Well, that's no good. The client, the pick first client will always reuse the same connection that it had if it already has a successful one. So if you close the xDS stream, it's just going to open it again on that same client. Okay, so can we just close the connection then? Well, the pick first client is always just going to go back through that list in the same order that it initially saw it. So even if you close the connection, that same host, its favorite host, is just going to go back to it, and it's going to open another connection again. Okay, fine, have it your way. Like, what we ended up having to do is basically, anytime a client tries to connect and sets up an XDS stream, we kill the connection, store that client's address in a ban list, and essentially say, if that client tries to reconnect again, we kill the connection immediately. What that means for the pick first client is pick first clients will basically recognize that a connection is bad if it can't do anything meaningful, like open the TLS connection, et cetera. So as long as that happens early enough, we're actually good to go. But I mean, this is obviously not a super ideal solution, right? We're really sort of counting on the semantics of pick first, and we really get this, this mess sitting right in front of the TCP port, and it's just not an ideal solution. So what do? Well, turns out, as we were working on this, gRPC got a little bit of an upgrade. The pick first strategy was upgraded to be able to support shuffling the IP address list. And that's perfect, right? It's just like round robin. It's going to pick a random address at the beginning, except that it's not actually going to open a new connection or a connection for every single target. Now, that's pretty much the long-term solution that we've got. It's slowly making its way through the system. But the problem is that some applications have really, really long deployment cycles, like multiple quarters sometimes. And turns out the longer the deployment cycle we have, it turns out most of those applications are also the ones with the biggest impact. So we really don't have much of a choice. So we have to keep this in for a really long time, even though the strategy is available today. So as a quick side note, I did want to mention that as a last resort, we ended up figuring out a way to dynamically remove the hosts that are at capacity from the DNS record. What that means for the clients is that they don't even see that IP, they never connect to it, and so we're looking at significantly more even distribution. The problem is that this doesn't really work for everyone. Not everybody's got the capability to do that, and I didn't want to focus on this talk on solutions that not everybody could do. It's also something that really messes with the way that we do alerting, and it's also got its own set of risks, so we really didn't want to do it, and this helped a lot, but it's ultimately slowly rolling out the new pick first strategy that's working out for us. So what are we at now? Just a little reminder, this is where we were at before. Some hosts taking 10 times the traffic, some hosts basically sitting idle, and this is what it looks like now. It's still not a super great spread because we still got a bunch of hosts in pick first, and so they're still picking their whatever closest hosts there are. But the spread is obviously significantly tighter, and it's getting tighter pretty much every day as the applications progress. So that custom listener code is still going to stay in because we still actually want to have a hard limit on how many resources a single host is going to use, but we're really looking significantly better, and finally, my fellow on-calls and I can get a good night's sleep. Before we close up, I did mention that we had to make sure that our XDS control plane was as performant as possible, and it's time for us to put our money where our mouth is. We're not afraid to hide it. So we actually open source it. So you can go check it out. It's basically we call it a Diderot, following the long-standing tradition of naming LinkedIn projects after philosophers. But the idea is it's really fast, it's super flexible, and it just offers you the XDS protocol implementation and a data structure that goes along with it. And then you pick what you give to the client. So it's actually completely unopinionated as to what your actual configuration is. And this is what we use to send Zookeeper data to RESTly clients over XDS. It's also got all the advanced features of xDS, like state-of-the-world Delta, but also supports glob collections, which is the new way to do cluster or like endpoint discovery. The other thing that we ended up doing is that because we had to squeeze so much performance out of each and every one of our instances, that we realized there's a pretty big hole in the gRPC Go implementation. There's a lot of memory leaks that could have been fixed with stronger like buffer reusing. And so the contribution that we made is basically allowing gRPC Go to reuse buffers from what it reads off of the wire all the way to the deserializer and vice versa, from the serializer all the way to the wire. And we're close to, or at least opening the door to, having a zero copy framework in the future. And it's checked in, so should be available in the next release. Everybody who uses Go gRPC should just be able to have it, no problem by default, for free, no strings attached. So in closing remarks, I hope you guys learned a couple things. Tried to make this talk as agnostic as possible in terms of what your actual infrastructure is or what your stack is. I didn't want the answer to be, what does it take to make something like this work at the LinkedIn scale? Oh, just write better code or throw more hardware at it. We covered a problem where you couldn't throw more hardware at it, though we did write a lot of really good code, but now you guys can have access to it too. And also really just wanted to express how important it is to have a deep understanding of how your stack works, how big problems can be solved with small things, but how small things can cause really big problems. Thank you. And I think we've got some time for some questions, yeah.
Thank you. So was the decision to write your own xDS server mainly motivated by also having to support your old clients, or were there other reasons as well?
That was a big one. We looked at using Istio for a really long time and basically using the Istio configuration language to generate all the Envoy configs, but forking overall the Istio code ended up just being like a really big hassle. It was too opinionated about Kubernetes, and so in the end, there were no good open source like Go control planes that we could use. So that was the main reason. Just we wanted to be able to not use it in the Kubernetes world.
Thanks.
The custom STS server that you wrote, I know in your redesigned stack,
Yeah.
Kafka also talking to the XDS. What protocol was it using?
Sorry?
What protocol was it using? Was it gRPC? I know XDS uses, we have gRPC client, REST client, and you have Kafka.
Right. So all the clients emit to Kafka, or the servers that want to announce they emit to Kafka, and then the control plane itself directly consumes from Kafka.
Okay.
Does that answer your question?
No, it doesn't. So I know when you had Zookeeper, it was
Yeah.
using TCP, right?
Okay.
But after Zookeeper was replaced with the custom XDS. So what protocol was it using under?
Oh, so that's just gRPC. That's just a gRPC bidirectional stream. That's why it uses pick first, and that's why we ended up in this situation.
Got it. Okay.
Yeah.
What kind of hack did you use to prevent gRPC from connecting to certain XDS control planes at the TCP layer?
So at the TCP level, as soon as you get the connection, we store the map of IP addresses that are banned. And if it's in that map, we immediately close the connection. So we have to wait for it to establish, but then kill it. And as long as that happens early enough, then it works out okay. Because
but how does gRPC detect that this connection, that it should go to another host, basically?
So the pick first client, it's going to try every single host on the list. And if the first host, it can't successfully establish the connection, it's going to go look somewhere else. So the server, the XDS control plane itself, isn't saying, go look elsewhere. It's just saying, you can't connect to me. So figure it out. But
how did you make sure that the subchannel never gets ready, basically?
If you close the connection early enough, like I said before, for example, the TLS handshake happens, it never gets ready.
Okay.
Yeah. Which is hairy. It's not great, but it just is what it is, yeah.
So if I understand the problem, in your pick first, if you have 1,000 number of servers to which your DNS is resolving, so was there a solution considered in which you would take a subset of those hosts which would be available, and then rather than in which you show 87%, 90% of the memory was using your TLS connections.
Yeah.
Like, was a solution considered in which you would still choose round robin, but with a subset of host to which your DNS is resolving?
So the problem is that, we'd have to have a pretty custom DNS solution, right? Where you have every application, I guess, is going to get a different subset. But the problem is that ultimately this is happening at like Envoy gRPC proxy list, they're just opening that connection. That connection isn't really configurable. So it's just going to pick whatever the default settings are.
But then how do you decide which one to choose? So for example, right, like one server could be in your SF, other server could be in your like Europe, and it's giving you all the DNS resolving to your 1,000 hosts, in which either one could be in US or other one could be Europe or any other location. Like, then how do you know which one to choose?
Yeah, so at LinkedIn, we're still on-prem, so we got 3 data centers, and there's a sort of data center global configuration where if you're in LTX1, you're going to get connected to the LTX1 control plane. Fundamentally, every control plane instance has to have the whole data. We couldn't really partition it out, so it's not like we could have done something like that either, where we could have just some hosts go to that partition because they might want to talk to some other service which is on a different partition, and that's not something that's compatible with the XDS protocol. So we couldn't even shard it well, unfortunately. But yeah, so the config that you mentioned, it's just per data center. Okay, I think we're pretty much just done. So thank you so much, everyone. Have a good one.